Methane is a potent greenhouse gas produced mainly by the methanogenic archaea. Although these are simple unicellular organisms, they use some very sophisticated chemistry to allow them grow and thrive in the low-energy anaerobic environments where they live. The so-called hydrogenotrophic methanogens get the energy they need by reducing CO2 to methane in a multi-step cycle. Recently, scientists of the Max Planck Institute of Terrestrial Microbiology and Biophysics have isolated and characterized a large protein complex that incorporates two steps of the methanogenic pathway. The first reaction of the cycle is the reduction and condensation of CO2 to an organic carrier molecule, and this represents a tricky challenge for methanogens because the available electron sources in the environment, namely hydrogen and formate, aren't sufficiently reducing to drive this reaction forward. This challenge can be met using a process called electron bifurcation, a reaction in which the energy of a pair of electrons is effectively split, so that one of the electrons becomes more strongly reducing than the other one. Electrons can enter the complex from formate via a formate dehydrogenase subunit, or indirectly from hydrogen via an organic hydrogen carrier known as F420H2. Using 3D classification of their particle images, the team found two different states of the complex that differ by a large rotation they call the mobile arm, allowing them to form a theory of how electrons move through the complex. In state 1, electrons move from formate or F420H2 down a chain of iron-sulfur clusters. From there, it looks like they make the jump to the bifurcating flavin, possibly with the help of some conserved additional cysteines. Once the flavin is reduced and following a conformational change to state 2, the more weakly reducing electron is transferred to the heterodisulfide reductase active site, while the more strongly reducing electron is passed to an isolated iron-sulfur cluster that seems to act as an electron shuttle. When the mobile arm swings back into state 1, this electron can be passed on via another long chain of clusters and finally to the CO2 reduction site. This result supports biochemical results, showing that electrons are transferred directly from electron bifurcation to CO2 reduction without needing a soluble electron carrier. 3 copies of the high-resolution dimeric structure fit into a larger cryo-EM map, giving rise to a beautiful hexameric structure. Although this is the first time that such a structure has been purified and studied, there are good indications from genetic organization and pull-down assays that this sort of structure is common in methanogens. In addition, existing crystal structures of both electron bifurcating and CO2 reducing methanogens solved by Tristan Wagner and Seigo Shima fit very well with the organization of those subcomplexes in the new 3 megadalton hexameric structure. So it seems that this structure might be a feature across many different methanogenic species. This, the researchers say, is part of what is so exciting about studying microbes, because there's such a lot still to discover about the unique ways in which they thrive in their environment, and in so doing, shape the world in which we live.